Hi class, welcome back. So this week we're going to study the derivative on Tuesday and the integral on Thursday. So this is lecture number 4, and today we're simply going to focus on the derivative and some rule to compute derivatives. So we said last time, I'm not going to rewrite the definition, but the derivative of given a continuous function from the set of real numbers to the set of real numbers, and continuous and differentiable, the derivative of f prime of x is equal to the limit for h that goes to 0 of f of x plus h minus f of x divided by h. So essentially what we're doing is that we're taking 2 points on a curve, one at location h, and then one at location x, and one at location x plus h. And then we're going to make h converge to 0, which means that the distance between x and x plus h becomes smaller and smaller. And we study the variation of y divided by the variation of x. So this is f of x, or y equal f of x, and this is f of x plus h. So this quantity is delta y, and this quantity is delta x, which is equal to h. So when h goes to 0, this point approaches this point, the distance in x becomes smaller and smaller, and we want to study what the slope of the linear approximation does. Now, we have seen some examples on how to compute the derivative using the limit of the incremental ratio. So if we take, for example, the function f of x equal x squared, then f prime of x is equal to the limit for h that goes to 0 of x plus h squared plus h plus x squared divided by h. Well, this quantity is x squared plus h squared plus 2 hx. So this is the limit of, sorry, here there's a minus sign. So this is the limit of 2hx plus h squared divided by h. We can simplify h, or we factor out h at the numerator and then we simplify. So what is left is the limit for h that goes to 0 of, well, this one here will go to 0, so this is 2x plus h, which is equal to 2x, and that's the derivative. Now, obviously, we don't use the limit of the incremental ratio every time we want to compute a derivative. We're going to see some of the rules that we can use for the computation of the derivative. Now, let's see an example of a function that is continuous but cannot be, but it's not differentiable. Well, the typical example is the function of the absolute value of x. Indeed, if we in the point x equals 0. Indeed, if we take the absolute value of x, the function looks, so f of x is equal to the absolute value of x, and we're studying x0 equals 0. So in this point, if x is equal to x0, then f is continuous, but f is not differentiable. Well, let's see why. Well, we know that we have seen last time that for a function to be differentiable, the limit must exist, the limit of the incremental ratio. So what we want to study, well, let's draw the function first. Well, if x is positive, f of x is equal to the absolute value of x, which is x itself. Then if x is negative, we take the absolute value, so the function x would be like that, but we take the absolute value, so we change the sign, and that's how the function looks like. Correct? Well, we're going to study, obviously, in all the other points, the function is continuous and differentiable. This is just a straight line. But in the point x equals 0, the function is not smooth. And we know that, or you should already know that most of, generally speaking, a function has to be smooth to be differentiable. So the function is continuous because obviously the limit for x that goes to 0 from the left of f of x is equal to 0, and the limit for x that goes to 0 from the right is equal to 0, and the limit that for x that goes to 0 from the left is equal to 0. So the two limits are the same, so the function is continuous. Which basically means that you can draw the function without interrupting your drawing, without jumping from one point to the other one. If we take, for example, a function like this, okay, so this is going to be something that is not related to this example. If we take a function like this function is not continuous in 0. This function is essentially f of x is equal 1 if x is greater than 0 and minus 1 if x is less than 0. And if you want, you can define it equal to 0 in the middle. But for sure, this function is not continuous in 0. Now, the absolute value of x is continuous in 0 because the two limits are the same. But we're going to prove that it's not differentiable. So in order to be differentiable, we want to verify if the limit for h that goes to 0 of the f of x plus h minus f of x divided by h exists, which is this symbol here. So that's the question that we try to solve. Now, x is equal to 0, so we're basically studying the limit of f of h minus f of 0 divided by h. Well, in order for a limit to exist, it means that the limit from the right must be equal to the limit from the left. So h goes to 0 plus, meaning h goes to 0 from the right. Must be equal to the limit from the left of the same quantity. Okay, having some issues with the Apple Pen today. Okay. Well, let's try to compute that. So I'm going to put a question mark here because that's what we want to prove, right? So we first compute this limit. So the limit for h that goes to 0 plus of f of x plus h minus f of x divided by h. Now, x is equal to 0. So here we can just say the limit of f of h minus f of 0 divided by h. Now, here, and this is pretty simple, we just have to replace the value of the function. So f of h is the value of the function in h, and we know that we're going to 0 from the right, so h must be positive, so f of h is simply equal to h. So this is h minus, well, f of 0 is the value 0 of the function, which is 0, divided by h. So this is h divided by h, which is equal to 1. This makes a lot of sense, right? Because the derivative is the slope of the curve. We're studying the derivative on the right side. It's this, if we're approaching 0 from the right. Well, on the right, on this quadrant of the Cartesian plane, this is a straight line, so the slope is equal to 1. Well, it's actually the identity, y is equal x, so the slope is equal 1. And that's the limit of the incremental ratio. Now, what we do is the limit for h that goes to 0 minus, which means we are approaching 0 from the left, so from this side of the plot. And here we do exactly the same. It's f of h minus f of 0 divided by h. Now, here we get that we are approaching 0 from the left, so h is negative, so we get minus h minus 0 divided by h. So this is minus h divided by h, which is minus 1. So the limit from the right and the limit from the left, they do exist, but they're not the same. So this one here is not verified, which means that this limit doesn't exist. So this is not verified, which means that this one here, this limit here doesn't exist. So the function is not differentiable because the left side and the right side limits are not equal. Okay, well, let's study, we're going to review very quickly all the rules for the differentiation. Well, I'm going to put them in red, and every time I'm going to do an example, although most of you are going to be familiar with those. So if we have the derivative of a constant value, this is going to be equal to 0. This is pretty straightforward. If you have a constant function, no matter what the constant is, the slope is equal to 0. The variation in y is, so if you write the slope as the delta y divided by delta x, well, no matter what delta x is, delta y is going to be 0 because it's c minus c. So the derivative is 0. The derivative of x is equal to 1. Well, again, this is straight line. So the slope in x, the increment in y is equal to the increment in x. So the slope is constant and is equal to 0, and is equal to 1. Well, in general, if you have a polynomial, this is going to be n times x power n minus 1. We could prove this one here using the limit of the incremental ratio, but we're not going to do that. I assume that you already know that, or you have already seen that in calculus. So if we write the derivative of x power 5, this is going to be 5 power times x power 4. This is pretty straightforward. If we have a function multiplied by a constant, then the derivative is the derivative of the function times the constant. So if we have the derivative dx of k times f of x, this is equal to k times the derivative of f of x. So for example, if you have the derivative of 6 times x power 3, this is going to be 6 times the derivative of x power 3, which is 6 times 3, 18 times x power 2. Well, and the derivative is also a linear operation, so the derivative of a sum of functions is equal to the derivative of a function plus the derivative of the other function. So the derivative in the x of f of x plus g of x is equal to the derivative of f of x plus the derivative of g of x. So again, if we go back to our polynomials, the derivative of x squared plus 3x is equal the derivative of x squared plus the derivative of 3x, which is equal to 2x plus 3. Now we have to do the product rule, which is probably the one that the students tend to forget more easily. So if we have the derivative of a product of function, so it would be f of x times g of x. Well, what we do is the first function times the derivative of the second function plus the second function times the derivative of the first function. Well, let's do an example. Let's say that we want to compute the derivative of 1 plus x times x squared plus 3. Okay? Well, this is going to be 1 plus x times the derivative of x squared plus 3 plus x squared plus 3 times the derivative of 1 plus x. Now, the derivative of x squared plus 3 is 2x, so this is 2x times 1 plus x. And the derivative of 1 plus x is 1, so this is x squared plus 3. So we get 2x plus 2x squared plus x squared plus 3, which is 3x squared plus 2x plus 3. Well, if you don't trust me, you can verify this one here pretty easily because you can do this product. So I'm going to write alternative method. We can write this one here as, so I'm going to rewrite the expression here. So this is the derivative of x cubed plus x squared plus 3x plus 3. Now we can do this derivative using the linearity. So we do the derivative of each single term and then we sum them up. So this is 3x squared plus 2x plus 3, and the derivative of 3 is 0. So this one here gave the same result as this one here. Now you could say the second method is much easier. I agree with that, but the chain rule is actually convenient when you cannot use algebra to simplify your expression here. Like if I put, if here I had some sort of exponential, for example, e power x squared, I wouldn't be able to simplify the expression and go down to one polynomial, so I would be forced to use the chain rule. I'm going to delete that since we haven't seen the exponentials yet, but the derivatives of exponentials yet. Well, then there's the derivative of the product of a quotient. So if we have the derivative of f of x divided by g of x, this one here is the second function, the denominator g of x times the derivative of f of x minus f of x times the derivative of g of x. So it's the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator divided by gx squared. So the denominator square. Again, we're going to do an example with polynomials. So if we have the derivative of x squared plus 3x minus 4 divided by 2x plus 1. Okay, this is going to be the denominator, 2x plus 1, times the derivative of the numerator. So I'm going to write it just for the first time. Minus the numerator times the derivative of the denominator divided by 2x plus 1 squared. Okay, so this is 2x plus 1. We're going to do the derivative first, and then we're going to solve the algebra expression. So this is going to be 2x plus 3, and then it's minus x squared plus 3x minus 4 times, well, the derivative of 2x plus 1 is just 2. So I'm going to delete the parentheses, and I'm going to put, well, I'm going to write it here, divided by 2x plus 1 squared. Okay, so now we're going to do the math here. This is pretty straightforward. It's 4x squared. I'm going to do it in one single step. So this would be 6x plus 2x, which is 8x plus 3, minus 2x squared minus 6x plus 8, divided by 2x plus 1 squared. I'm going to wait to develop the denominator just in case I can simplify with the numerator after we do the algebra. So this is 2x squared plus 2x plus 11 divided by 2x plus 1 squared. I guess there's nothing we can really do here. So if you want, you can develop the denominator, but so it's 4x squared plus 4x plus 1. And that's the result of the derivative. Well, what if we have irrational functions? So, for example, we have a square root. Well, I'm going to write it as a rule, but it can be derived from the previous rules. So the derivative of the square root is 1 divided by 2, the square root of x. Well, if you want, you can actually derive this one here from the previous rule, because you can write the square root as power 1 divided by 2. So this would be 1 divided by 2 times the square root of 1 divided by 2 minus 1, which is 1 divided by 2 times x power minus 1 divided by 2, which is 1 divided by 2, 1 divided by x, 1 power 1 divided by 2. And then this is 1 divided by 2 times 1 divided by square root of x. So this is essentially, it's not really proof. Well, that's I guess the proof, but they simply used this rule here, where n was actually a fraction. Okay. Well, we have already seen exponential functions, logarithmic functions, and trigonometric functions, so we can actually study the derivatives of these functions here. The derivative of the exponential is actually the easiest one because it's equal to itself. But again, remember that most of the time we don't study derivatives like that. We study functions of functions. So for example, well, if we have the derivative of 3e power x, we're just going to use the rule of the product of a function with a constant. So this is 3 times the derivative of e power x, which is 3 times e power x. If we have the derivative of e power x divided by x power 4, well, here you have two options. You could use the quotient, or you could do the product, rewriting this one here as the derivative of e power x, x power minus 4. Well, if we do that, we just have to use the rule of the product. So this rule here, we're going to take the first one as it is and then multiply it by the derivative of the second one. So this is the derivative of x power minus 4 plus x power minus 4 times the derivative of e power x. Now this is going to be, well, we do this derivative here. This is going to be minus 4. So it's minus 4 times e power x times x power minus 4 minus 1, which is minus 5, plus x power minus 4 e power x. And then if you want, you can factor out e power x, and this is x minus 4 minus 4x power minus 5. Well, if we have the derivative of 2 times e power x minus 3 divided by x, well, here we have to use the linearity of the derivative. So we're going to do the derivative of this one here minus the derivative of this one here. The first one is pretty easy. It's 2 power times e power x, because the constant multiplies the derivative of the function, and the derivative of the function is the function itself, minus, well, this one here is x power 1 divided by x is x power minus 1. So the derivative is minus 1, so it's going to change the sign. So it's plus 3x power minus 2. Okay, now the derivative of the logarithm. Of the log of x, assuming that the log is in the natural base, so e, well, this is 1 divided by x. So if we have, for example, see the derivative, if we have, for example, the derivative of x times the log of 2x, well, I haven't shown you the one rule yet, so let's wait to do this. Let's simply do x times log of x. Well, this is x times the derivative of the log of x plus the log of x times the derivative of x. Well, this one here is x times 1 divided by x plus log of x plus x. Can simplify. This is 1 plus let's write it this way, x times log of x. The derivative of x is 1, so this is log of x. So let's redo this step. So the derivative of x is the derivative of log of x is 1 divided by x, so this is x times 1 divided by x, plus the derivative of x is 1, so this is log of x, and then we simplify x and x, so this is 1 plus log of x. Okay. Well, we have the derivative of the trigonometric functions, and then we're done with all the main functions that we're going to use in this class. The derivative of sine of x is cosine of x. The derivative of cosine of x is minus sine of x. The derivative of tangent of x is 1 divided by cosine square of x. And then the usual rules apply. So if we have, for example, the derivative of a sum, say for example 2 sine of x minus 7 cosine of x, well, this is 2 cosine of x, because the derivative of sine is cosine, minus, but then we change the sign because the derivative of cosine is minus sine, so this is plus 7 sine of x. The derivative of tangent of x minus x is equal to 1 divided by cosine square of x minus 1. The derivative of x cosine of x is equal to, well, I'm not going to write all the steps. The derivative of x is 1, so here we are left with cosine of x, and then the derivative of cosine is minus sine, so it's minus x sine of x. Okay, now what happens if we have a function of another function? So for example, if we have something in the form the log, or, well, I guess I use the notation ln. So the natural log of x squared, or the natural, so f of x is equal to the natural log of x squared, or e power 1 divided by x. Now, x squared is a function itself, and 1 divided by x is also a function. So what we have to study is what we have to use is the chain rule. These functions here can be written in the form f of x, f of g of x, because we take x, we compute the function g of x, and then we apply another function to the result. So here, for example, in the first example, we take x, we compute x squared, and then we compute the log of x squared. In the second example, we take x, we compute 1 divided by x, and then we compute e power 1 divided by x. So this is essentially a function of a function. So in order to do that, we're going to use the chain rule. Which is actually pretty simple. The derivative in dx of f of g of x. Well, just in case if you're wondering why, in calculus 1, essentially we always study functions of one variable, so we always compute the derivative with respect to x. But in calculus 3, for example, you can have functions of two variables. For example, any function in the geographic space is a function of latitude and longitude. And so we can compute the derivative in one direction and the derivative in another direction. Maybe we're interested in some variations north-south, or some variations east-west. So this is a little bit redundant to clarify every time that we're computing the derivative with respect to x. But this is only because in calculus 1 we deal with functions with one variable. So this is going to be the derivative of f computed in gx times the derivative of g of x. So let's do a simple example. Let's say that we have the derivative in dx of the log of 3x plus 2. Well, first of all, we're going to compute the derivative of f, and we're going to evaluate that in 3x in g of x, so in 3x plus 2. So this one here is, we know that the derivative of the log of x is 1 divided by x, so this is going to be 1 divided by 3x plus 2. And then we have to multiply by the derivative of 3x plus 2. So this is 3. So this one here is g prime of x. And this one here is f prime g of x, evaluated in g of x. So we can rewrite actually this rule here in a simpler way using the prime symbol. So what you want to do is compute the derivative of f of g of x this is going to be the derivative of f, the derivative of f computed in g of x times the derivative of g of x. So in this notation here, it's probably simpler to remember. So this rule comes pretty handy even with polynomials, because let's say that we have something in the form x squared plus 5 power 3. Well, if we could actually do the cube of this polynomial here, which would be something in the form x power 6 plus 15 times x power 4 plus 75. So this guy here would be, let's see, x power 6 plus 15 times x power 4 plus 75 x squared plus 125, if I did the math right. Well, we do the derivative, and we get 6x power 5 plus 60x power 3 plus 150x, something like that. But you see that the math is not, the math is not complicated, it's just algebra, but you have to remember the rules of the rule about the cube of a polynomial, and then you have to do some high order exponentials there. Well, what we could do, we could apply the chain rule. So we can see there are two functions here. We take x and we compute x squared plus 5, and then we take this result here, I'm going to call it y, and we're going to compute the cube of y. So one function is, let's say f of, I'm going to call it with a different name, u, or well, y is fine, equal y cube, and another function g of x is equal, so y equal g of x is equal to x squared plus 5. So this is how we compose the composition of the two functions. So at this point, this would be, if we want to compute the derivative using the chain rule, well, we first have to compute the derivative of this polynomial here, which is a cube. So this would be 3 times x squared plus 5. And then we have the derivative of the polynomial here, which is 2x, and that's it. So this one here is the derivative of x squared plus 5. This one here is the derivative, I'm going to call it in dy, of y cubed, where y is equal to x squared plus 5. So if we do the math, we're going to get sorry, I forgot a square here. So the derivative of the cube is 3 times this function here, power 2, 3 minus 1. So now this is 3 times x power 4 plus 25 plus 10x squared times 2x. So this is 3 power 3 times x power 4 times 2x, which is 6x power 5. I'm going to do this one here first. It's going to be plus 30 times 2 is 60, x power 3 plus 25 times 2 is 50 times 3 is 150 x. So we got exactly the same result, but now we use the chain rule. Now in this case here, probably it's simpler to, if you remember how to do the cube of a polynomial, it was simpler to do it this way. If you didn't remember though, you could use the chain rule as well. So the idea here is that if we have something in the form d of dx times x power, let's say n, this is going to be n times x power n minus 1. So if you have something in the form, if you replace f with a function, d in dx of f of x power n, this is going to be n times f of x, oops, n times f of x power n minus 1, and then you have the derivative of f of x. The chain rule comes handy when we compose trigonometric, exponential, and logarithmic functions with polynomials or with other functions in general. So I'm going to write here some of the compositions. You can actually derive them but just applying the chain rule, but well, I'm going to write them in green. So, well, this one here was the first one. Then if you have the derivative in dx of sine of f of x, so you're going to have the derivative of sine is cosine, and you compute it is in f of x, and then you have the derivative of f of x. If you have the derivative of cosine of f of x, well, the derivative of cosine is minus sine, so this is minus sine of f of x times the derivative of f of x. The derivative of e power x, e power f of x. Well, this is e power f of x because the derivative of e power x is the function itself, times the derivative of f of x, and then the derivative of logarithm of f of x is equal to 1 divided by f of x, which is the derivative of the log, times the derivative of f of x. Well, I guess I should have written this one here in green too to be consistent, so I'm going to write it here. F of x power n is n times f of x power n minus 1 times the derivative of f of x. So let's see a couple of examples again. If we have the derivative of sine of x squared plus 1, this is going to be cosine of x squared plus 1 times the derivative of x squared plus 1, which is times 2x. So you can write it as 2x times cosine of x squared plus 1. The derivative of e power x squared plus 2, it's going to be e power x squared plus 2 times the derivative of x squared plus 2, which is 2x. So again, 2x times e power x squared plus 2. The derivative of log of x squared minus 3, this is going to be 1 divided by x squared minus 3 times 2x, which is 2x divided by x squared minus 3. The derivative of 1 divided by x squared plus 3 power 4. Okay, now here what I would do is rewrite the function first. So I would write it as x squared plus 3 power minus 4. Then we do the derivative of this power here. So this is going to be minus 4 times x squared plus 3. This is minus 4 minus 1. So I'm simply going to write minus 5. And then we have the derivative, and then we have the derivative of this guy here, which is 2x. So this is minus 4 times 2x, which is 8x, divided by x squared plus 3 power 5. Okay, let's do something a little bit more challenging. although I don't think we're going to study such complicated functions, but we're going to have the log of the sine square of 2x plus 3. So this one here is a complicated function because we take x, we compute 2x plus 3, we then compute the sine of 2x plus 3, we then compute the sine square of we compute the square of the sine of 2x plus 3, which is equal to this. It's just a different notation for the sine square. And then we compute the log of this quantity here. Okay, so we have to do it step by step and do it a couple of times at least. So the outer function is the log. So we're going to take 1 divided by the sine square of 2x plus 3, and then we're left with derivative of the sine square of 2x plus 3, which is again equivalent. This one here is the same as writing d and dx of sine of 2x plus 3 all squared. This is just a different notation. So now we have to take the derivative of the square. So this is going to be 1 divided by sine square of 2x plus 3 times 2 sine of 2x plus 3, and then we have the derivative of whatever is left, which is the sine of 2x plus 3. Okay, so we have 1 divided by sine square of 2x plus 3 times 2 times the sine of 2x plus 3. Okay, we have the derivative of the sine, which is cosine of 2x plus 3. We're not done yet because we have the derivative of the argument of the sine, which is 2x plus 3. So now it's 1 divided by sine square. We can simplify, of course, so I'm going to do everything at the end, times 2 times the sine of 2x plus 3 times the cosine of 2x plus 3. Now the derivative of 2x plus 3 is 2, so we multiply it by 2 here. Now the sine square can be simplified with this sign. We have 2 and 2, so it's going to be 4 cosine of 2x plus 3 divided by the sine of 2x plus 3. We simplify the square, so we are left with one sine at the denominator. So this is how it works when you have a complicated function. You have to do it step by step. You take the derivative of the outer function, the last one that you compute, and then you are left with a derivative of another function, which might be a function of a function, so you apply the chain rule one more time. In this case, you could have used the log property. So the log of the square could have been written as 2 times the log, so you would have skipped one step, but it doesn't really matter. It was just to prove a point to show an example of the chain rule applied several times. Let's do one more example. So we do the derivative of e power x plus 1 times the log of x squared plus 1. Okay, so we have a product first. So first we're going to do the product, right? So this is our function, and here there's a product. But each of them is a function of a function. So I could write this one here as f of g of x, and this one here as h of k of x, something like that. Okay, so, but first we have the product to do. So this is going to be ex plus 1 times the derivative of the log of x squared plus 1 plus the log of x squared plus 1 times the derivative of ex plus 1. Okay, so let's do now the, let's apply the chain rule. This is going to be 1 divided by x squared plus 1, and then we have the derivative of x squared plus 1, which is 2x. Then we have the log of x squared plus 1, the derivative of the exponential itself, so it's e power x plus 1 times the derivative of the exponent, which is 1. So this is like this. Now if you want, you can factor out e power x plus 1. And we're left with 2x divided by x squared plus 1 plus the log of x squared plus 1. Okay. I was checking my notes if I did it right, but yeah, it is correct. I think I did all the examples that I wanted to do. Now, why do we care about this? So the reason is that the derivative of a function allows us to understand if the function is increasing or decreasing. So let's see what this means. Okay. So let's say that we have a function from the set of real numbers to the set of real numbers. So the title here is going to be increasing or, well, and decreasing functions. So if well, we say that f is increasing if x1 less than x2 implies that f of x1 is less than f of x2. And f is decreasing if x1 less than x2 means that f x1 is greater than f of x2. So for example, we take the function cube of x cubed. This is a strictly increasing function because if I take x1, for any x1 less than x2, f of x1 is going to be less than f of x2. So as long as x1 is less than x2, then f1 is less than f of x2. Well, if we take a parabola, so f of x equal x squared, the function is, so if x is greater than 0, f is increasing, because I take x1 here, x2 here, and then their image increases as well. Instead, if x is less than 0, f is decreasing. So if I take here x1 and here x2, now x1, in this case, x1 is less than x2, but f of x1 is greater than f of x2. Instead here, x1 less than x2, and f of x1 is less than f of x2. So for some functions it is pretty straightforward. If we take the parabola, it's decreasing when x is negative and increasing when x is positive. The cubic function is increasing in all the set of real numbers, in the entire set of real numbers. If you take, for example, f of x equal 1 divided by the square root of x, well, this function is defined only for x greater than 0, because we cannot define greater than or equal to 0. Well, actually, it's x greater than 0 because x is at the denominator. So I can compute the square root of 0, which is equal to 0, but then I cannot do 1 divided by 0. So the domain is x greater than 0. We're going to do the domains of the functions next time. Now this function here, well, the limit for x that goes to 0 plus of 1 divided by the square root of x, well, this is 1 divided by 0, which is plus infinity. So it's here. The limit for x that goes to plus infinity of 1 divided by square root of x. Well, if the square root of x, if the square root of a big number is a big number, so 1 divided by a big number is 0, and it's always positive, so it's going to be here. So the function is more or less something like that. Well, actually, the kick is a little bit so it drops down very quickly, and then it goes to 0. So this function here is decreasing in the entire domain. Well, in some cases it's a little bit more complicated because drawing the graph is not that simple. So we can use the derivative to study when the function is increasing or decreasing. So I'm going to write theorem, although it's essentially a result that we're going to use without proving it. So let's say that we have a function from the set of real numbers to the set of real number, and it is differentiable. Otherwise, we cannot compute the derivative. Now, if the derivative of x is greater than 0 for x in, let's say, an interval of the function, then f is increasing in that point. If f prime is less than 0, then f is decreasing. And if f prime of x is equal to 0, then it means essentially that the function is flat. So it's not increasing nor decreasing. So we reach a stable point. Well, let's see how we can use this result. So we're going to do an example as usual. I take f of x equal 27x minus x cubed. So I took a function that it's not easy, it's not straightforward to draw. Well, I want to establish when it is increasing and when it is decreasing. Okay, so I took a function which is defined on the set of real numbers. So the domain is the entire set of real numbers, and actually the function is differentiable everywhere. It doesn't have any discontinuity or any point where the function is not smooth. So what we want to do is to study where the function increases and where the function is decreasing. So we study the derivative of this quantity here. Well, this is 27 minus 3x squared. Now what we have to do, I'm going to call this one here f prime of x for simplicity. So we want to study when f prime of x is greater than 0, and that's why we reviewed quadratic inequalities at the beginning of the class. So we want to study 27 minus 3x squared greater than 0. Well, if you want, you can factor out 3. So this is 9 minus x squared greater than 0. So now, well, 3 is always positive, of course, so we just study 9 minus x squared greater than 0. So the way we do it, either you plot the parabola, or you can also write this one here as 3 minus x times 3 plus x greater than 0. Now, this is a product, so in order to be greater than 0, either they're both positive or both negative. So 3 minus x greater than 0 means that minus x is greater than minus 3, which means that x is less than 3. And 3 plus x greater than 0 means that x is greater than minus 3. So what we can do is simply study what happens for each of the component of the product. So in the first case, so I'm going to call this one here 1 and this one here 2. Well, in the first case, this element is positive when x is less than 3. So from here, from minus infinity to 3, this function here is positive. So I'm going to do a solid line, and then it's negative otherwise. So it's positive here, negative here. The second one is going to be positive when x is greater than minus 3. So it's positive here, and it's negative here. Now here the two have different signs, so this is going to be negative. Here they have positive signs, so this is going to be positive. And here they have one is negative, one is positive, so the product is going to be negative. So f prime of x is greater than 0 when, well, if x is in between 3 and minus 3. So this means that f is increasing if x, well, f of x, if x is greater than minus 3 and less than 3. So what the function does, well, we know that we can actually study the limits too. The limit for x that goes to plus infinity of 27 minus x cubed. Well, x cubed is going to go to plus infinity, and then there's a minus sign, so it's minus infinity, so the function goes here. And the limit for x that goes to minus infinity of 27 minus x cubed is equal to minus infinity cube is plus infinity, is minus infinity with a minus sign is plus infinity. So it goes here. So, and then in minus 3 and in 3, they change the sign. So the function goes down here, it goes up here, and then it goes down again here. So let's compute the value in these 2 points. So in plus 3, this is going to be 3 power 3 is 27. 27 minus 27 is 0. And in minus 3 cube is minus 27 plus 27 is going to be 54. So that's essentially what the function does. Okay, I guess, well, we reached the end of the class. So next time we're going to look at the integral, and then there's going to be one more lecture, and then we're going to start looking at different functions and how to sketch them, and then we're going to switch to a different topic.